Hope it's all okay.
Yeah, maybe is that stop now?
Yeah, well, it's,
That's
at least you're not leaving until tomorrow night. Like if you were leaving first thing tomorrow morning, then even worse. But this way, there's a little bit of time, hopefully, that they can figure out, repair them enough to get back to Brazil, and then.
Yeah, maybe just to fix in the position and then do any procedure in Brazil.
Because really, you want to, if at all possible, you want to be doing medical treatments in your own environment where you know the people, you know how things work. Yeah, so get back in. That's always the good thing about traveling, right? It doesn't matter where you go, but the moment that plane touches ground on your own country, there's this sigh of relief, like, okay, I'm home. Things could go wrong, but not nearly as badly as if you're in some foreign country and you don't know the language, you don't know the culture. And it's a good sketch. Okay, so the plan then for this afternoon, I'd like to hear from both Sergio and Tiantian. Talk as much or as little as you like, but just to put forth what your problem is, what things you're thinking about, and then anybody else. We're just going to have it free. It's kind of like an open mic. And then once that's done, then we'll just open up a few apps. And I think our goal with the apps is just to kind of help reconnect you. So we're going to try to ask one or two questions and have you open something up and just explore a little bit, kind of get over that initial hurdle. And then once you do that, then everything else will be fine. And then that'll probably take us till coffee. And then we'll just break for coffee, and then we'll come back and just have a few closing words about, the future and some comments. And that should be it.
I have some slides in the end, right?
Perfect.
And Sergio, is it okay if we record this, or would you prefer we demo? It's okay? Okay.
Yeah. It's UH. This one?
Yeah.
Yeah.
There we go. Excellente. Yeah, I had to remove the remote, but you can just advance on that. And there's a pointer here.
Okay, thank you.
Okay.
Well, I bring here some cases with facing our group, non-seismic group in Petrobras. And here I separated some case in this block I call, is EM applicable to these issues in here? And there's another one just for comment from Doug and everyone else. The first one I want to bring here is this case in find gas accumulation using time domain electromagnetics. This case is in an area onshore Brazil, with almost a complete lack of information from seismic and borehole, and old oil field production, where the guys want to know where is the new areas to prospect this gas, but they want to know to get something to start, yeah. And they asked us to find any solution, a cheap solution, for they get a point to start, and said that his accumulation put this schematic section here, where the place this oil fields then is more than 5 kilometers below the surface, and they said that it's almost always associated with gas plume above the accumulation, and so we think about mapping this gas plume by mapping, instead of mapping the hydrocarbon, we map the pyrite that forms along with this plume. So we're thinking on using time domain electromagnetic for that, because pyrite is conductive. Yeah. It's not gold, it's pyrite. And this is the first problem. I just bring this just for us to comment or to discuss if it is feasible, our idea or on using time domain, or in this case. I put a guess of mine. I don't know exactly the value of the top of the spiritization. So I put.
Do they have any well logs that they
No.
like how much pyrite there might be there?
How much pyrite?
Yeah, like what concentration of pyrite you might expect.
Yeah, I don't know that information.
Is it going to be captured about like if you got a, let's say, clay layer somewhere in 100 kilometer range? Then
the top of the
like,
clay?
Yeah, then is it going to be like a captured on the
No.
No.
In some areas, it's included exuded through the surface.
Oh, okay.
Yeah, the gas.
Okay.
Sand is only sediment sands, and
So for the surface case, like you guys have seen like some plumes coming up to the surface.
Yeah.
Have you guys like did some lab measurements for conductivity or IP or any like property sort of experiment?
No perform any experiment on that.
Are you planning to do that?
Yeah, we are planning. We suggest to them the time domain. Yeah.
And what is the size of that plume?
Size?
Just the size. Like scale.
Maybe tens or hundreds of meters.
Is there a characteristic geophysical, geological, geochemical model that would start with a hydrocarbon source, and just to have some idea about what happens to actually get the pyrite, and then what concentrations of pyrite you might expect? I mean, do they have are there models like that around?
The geochemical model, we don't did that. It's also eventually it's observed at the surface, this pyrite, but we also expect that in another areas, in very other areas, it's not goes up to the surface. So it needs the knowledge of concentration and for constraint a model for time domain.
As we mentioned before, both the Russians and the Chinese seem to be using IP quite a bit for this. And I guess they must have some degree of success because they've been doing it for many years. But I've never really seen anybody say, okay, here's a characteristic model. For instance, in the mineral system, you have a porphyry deposit. Then there's kind of a characteristic model of a central core, and the alteration products that you have on the outside and what they are. And similar is true for the kimberlite pipes, right? They're sort of a cartoon model, but that's enough to kind of get you going to sort of see
I know that.
something to actually do numerical modeling on and see if you could
Yeah.
see something.
Okay, yeah. It's because I'm not get my material here. I don't bring with me this, so I push out of my mind a lot. I remember this case. Yeah. Well, it's one case I bring. I bring another.
I
thing,
maybe just make one comment. I mean, if it actually gets up to be shallow enough, then maybe surface like DCIP could potentially help. The benefit of doing the DC IP is that you've got a long enough time to charge things up.
Okay, I understand.
You can do it in a time domain system too, and especially if you control the waveform so that you're putting a current in that's just sort of constantly increasing, just so that you've got enough electric field that's going into your. So there is some potential of doing that, but again, to kind of tailor your transmitter, which needs to have a lot of power, so you might need a pretty big loop, and then.
What about 100 a square with 100 offside?
I don't know.
Maybe.
Again, you need to kind of have some idea what the dimensions of the target are that you're looking for.
It depends on the dimension.
Yeah.
Okay.
Like using an inductive loop, I think the layering, like a layer is a good target, but it seems like 100 meter is not that big. So yeah, it depends, but I think it's much. It'll give you a much smaller response compared to a big layer.
Okay.
So, yeah, I think to try some simulations.
And I get this other problem is quite common in onshore basin of Brazil. Is the problem of the seals in our onshore basins. And this is an example of Paraná Basin. It's the south of Brazil, where you also have this problem of a top basalt. It's a huge lava flow from Cretaceous and 200 meters thick. And we are looking for an area over here where this basalt is 1,500 meters thick, and the basement is almost or more or less 500 meters. And we expect to, by using MT and time domain, to map some interface. Here, only an example of the seismic the guys got this area. The seismic itself show almost nothing in terms of reflector the interface, and they decide that it can interpret the base of the basalt. But we expect to, by using this combination of methods, to help them mapping this interface, the top of basalt, which touch the tertiary sediments, the base of basalt, and the basement of the Paraná Basin. By using these methods, but the guys say that the real issue for them is in fact the seals. They have a lot of seals in the schematic model here. Those are seals, and they really don't know how to image all these seals with seismic. They can't get the image for the seals, and they need some help from another method. But we say to them that with magnet telescope north, then we also can't see the seals.
That's hard.
It's too hard. And the question is if there is another EM method that can help in this situation. So quite a hard situation.
Are there boreholes through there?
Yeah,
So
yeah.
there's potential.
Not too many, but there are a few.
Well, you need
Include-
to see deep, so, you know, you need to have that MT signal, I think, to see down to those depths. So it's pretty hard to get sort of resistive sills with the impedances. There's a little bit more of a chance maybe by using tipper information, which is more sensitive to lateral changes of conductivity. I didn't talk about it very much, but I mentioned there was this ZTEM survey, Z-axis tipper. So basically what that does is look for changes in the vertical compared to the horizontal field. And that's actually pretty sensitive to structure. And so if you have a resistor there, tipper information can sometimes see that resistor.
And typically, the Z10 can see in that depth.
That's pretty deep.
Yeah, that's quite deep. I think I think we're still about 30-ish, I would say.
30 hertz.
So I think that's
low.
quite deep. 4,000.
But you do have 2,000 ohm meters
That's
of
true.
basalt, so you see through the basalt perhaps pretty easily.
How about low 10?
Yeah.
But like CSCM on that.
Yeah.
I think we've shown one piece.
Yeah, the one.
The India case history.
Ah,
It's just quite deep, like pretty dead. You need a pretty large line source.
And still have this basalt over.
I mean, this is.
It's true. Yeah, it'll
It's not
generate
unusual.
it'll generate a huge response.
Okay.
So I think we're not sure. Yeah, that makes a challenge, right? Like you got a big resistor up top, and have another resistor below that you want to find. That's
There is, in this base, there is some 2D MET data that already proved that this interface is quite well defined by the.
Yeah.
right.
That should be an easier target to go, because you're going from a resistor to a conductor. Seeing the top of a conductor,
Sure, yeah.
that's pretty good.
And because of that, don't have none of that data have enough time or frequency to also none of them could see the basement, but it's all matter of the parameterization issue.
Well, those are pretty thin
Yeah, 10
cells.
meters there.
Yeah.
And why are you so interested in them?
I believe that the play of the guys is associated with these guys.
Okay. So those are your hydrocarbon zones.
Yeah. We helped them with the dikes, which are vertical structure, but we using magnetometric data in mapping. The dikes appears quite well in the map, map.
Because ordinarily you think about oil sort of having resistivity of sort of 100 ohm meters, and these are really resistive. So it's that you've got cells there that are really resistive, and they also happen to have some oil.
Yeah.
But you're not finding a resistor that's actually connected with the oil, with the hydrocarbon itself.
Sure,
It's
yeah.
hosed.
Okay, so what else we get? Well, here is another example. Now it's offshore Brazil, in Espírito Santo Basin. These are some blocks we got there. And Matthew, you could help me the size of these blocks?
25 per 25.
25 kilometers, okay. And here put a scheme aqui, just a scratch of all the anoctonal salts we have.
Oh, okay. Oh, wow.
It's just a scratch. We have plenty of salt, I call salt drops, because like drops, like this one. Yeah, many. And we have many small CSM survey spreading all this area, but all small 3D. Eventually, they put the pass over one of these drop of salt and can image quite well the shape of the salt and also the top of the salt.
Okay.
Yeah. And the question is how if we use this information of resistivity to make kind of resistivity to seismic velocity conversion to generate seismic velocity cube here. We already did a so simple study that gave us out kind of good results by only using a direct formula by this guy I.C. Kolu. That is right with Gary Mavico. It's a direct spectrophysics formula that converts resistivity back to velocity, seismic
What
velocity.
is rho? Go ahead. Rho R and rho S stands for, Sergio?
Rho R is rock, and rho S is
Salt.
no. It's only the rocks, the surrounding rocks. I believe it's saturated and is on the matrix. Yeah, the rocks. Yeah. And we generate in one of these CSM survey that get the one droplet of salt. We make a velocity model and feed it using the seismic analysis, and it improve the quality of the seismic. But I bring this example here because you showed a case history where you use a kind of different way of do this resistivity to seismic velocity. That one you.
Is that the Wadi Saba one?
I believe so. The conjugate gradient, yeah.
Oh, right.
Wadi
Saba.
Saba.
Yeah, Wadi
Yeah.
Saba. Yeah. So I think that was with the tomography inversion
Yeah.
and resistivity.
So I only bring so just for
Yeah, but that
highlight that we could use that.
But that wasn't, there wasn't a rock physics model built into the results I showed, although there was the potential for doing that. The inversion I showed you made use of the similarity in the structure between the resistivity and the seismic.
Yeah. This approach works pretty well. The problem is because we don't have enough CSM data for help them in all the areas they can. But if you did this approach is already a good tool for them.
So here the final product is the kind of migrated section.
Yeah,
Right?
sure. Yeah.
And how well, well, if you can get exact velocity model, that's the greatest case. But how well, do you know the velocity structure? If you got a kind of some sort of blob on that salt location, is that like a fine, or what kind of
Yeah, first of all, because the CSM can find the drop of salt, and in seismic, your seismic node can find the salt drop if you put a wrong velocity model. Only by put the salt in the right position and convert it to velocity, it helps. Already helps. Yes. Oh yeah, it's one more case. This is our first salt place, which is a huge accumulation of oil we have in Brazil, which is almost 7 kilometer depth, and below a thick layer of salt. And we see no way to use the electromagnetic methods for help or sounding this portion of the salt. And we think in using maybe the wells which tight hair, or the distance between wells is more than kilometer. The distance between wells in pre-salt areas.
3 kilometers.
3 kilometers. Yeah. But so we think on how if you use one well of this for doing kind of what I call this. What do you think about this idea? You know, I put a skin here.
So it's in marine, right?
Yeah,
It's
marine.
in,
Deep waters.
Yeah, this one.
okay.
Well, that's 3 kilometers. That would require modeling, I think, to answer if that's feasible or not.
And
what are you? I guess What are you trying to image? Like, what are so if you were to run a borehole to surface or surface to borehole, what are the questions you're trying to answer from that?
Try to sound this area below, just below the salt, somehow, with sensor in the borehole, and source it on the surface, or vice versa.
And is it conductive
This area
or resistive?
It's resistive.
That'll be
Below another resistive body.
that's tough.
Yeah, it's really tough. That work by Daniele Colombo, you showed, they acquire a big, huge CSN data and magnetotelluric also.
Yeah, but
Here we don't have any CSN data over this area.
it's pretty deep, like the 5 kilometers is quite. I think
To detect oil in the pre-salt unit is quite difficult because it's too deep. We have a huge resistor above, and the reservoir is carbonated. But we have some areas that the salt layer is not so well behaved. It's have some domes, walls. Right. So in these areas, it's not the case of this area because you have a pretty good image. But in other areas, when the salt becomes more complex, the silent image is it's an issue. So the magnetotelluric, for instance, can help to constrain the velocity model.
Right.
I think that's a good use for magnetotelluric.
That's.
And is the basement conductive?
No, it's resistive at almost. The real challenge we have.
So what's sort of like your plan? Like we're thinking about the surface to borehole or borehole to surface. Here.
Actually, we see no way to use electromagnetic in this area yet. Try to figure out our kind of way of using this method in this area.
And the question here, was whether you have a certain layer has an oil or not. Is that the question, or what's?
No, we know that there is oil here.
Okay. And then
we want to characterize it better. This fields, the extension of the oil.
Oh.
Such things. Yeah.
Oh, I see.
What do you have available for being able to carry out forward modeling, simulating things like this in 3 dimensions?
Forward modeling.
Yeah. Do you have software?
Yeah, we do. We already performed some investigation, synthetic investigation, but we don't get yet good results.
No, but just from the point of view of forward modeling and seeing what responses would be for various situations and different sources and receivers, to try to see if you,
Okay,
if
only,
you can see something.
only by using magnetotelluric in this case, yeah. Because with CSM we can't reach this version.
No,
But we
my
did
question was availability within Petrobras for actually carrying out 3D simulations for either controlled source or natural source.
Yeah, we do, but not in this area.
Do you have a code to run?
Algorithm.
Yeah,
Yeah,
we are
code to
good.
run it.
Yeah, we use that.
Is that a finite difference, finite element?
Finite difference. Yeah, the main software we have. We have another finite elements by Gary Key, that one written by Gary Key.
That's a 2D.
Yeah, but now he in Colombia he's developing a 3D
Okay.
3D version of that code. So that's it. Our challenges.
Yeah, those are challenging problems, difficult.
Yeah, that's why they are challenging. We have our jobs. And sorry about the slide. I make it quite quickly yesterday night.
That's great.
So what's your path forward with respect to these problems? Which ones are you planning to work on, and what are you planning to do?
We tackle this area only by mapping the pore salt, which we call all the pack of rock system above the salt. And we expect to, when we best characterize the package above the salt and generate also a velocity model, we can increase the quality of the image below.
Yeah.
It's our only approach by now in this area.
Thanks, Sergio. Jensen?
All right. Oops.
So I'll just need.
Yeah, I didn't prepare any slides.
That's fine.
Sorry about that. So.
This Blackboard, Go ahead, let's see, so we're going to just look for resistor. And yeah, so it was just within the half space, right? Yes.
You want to first show, like, go back a step and show which app we're opening?
Yeah.
But like, sorry, for the index page.
Yeah. So give us some. We don't seem to have very much for markers here, but we'll use what we've got. So what I'd like to do now is let's just kind of regroup a little bit and try to think of one or two questions that we might use, just kind of connect you with, with the apps and some of the material that we got, just to kind of bring things back. So there's a host of apps that are given. They're accessible through GeoSci, and yeah, go to our index.
Your binder?
Yeah, or just at least show one here and then.
So here's a list of the apps you've signed onto here before, but we've got some for DC resistivity. So there was quite a few that we talked about there. Let's see. So we did that layered earth, and that's where we kind of saw where the currents are and the charges for a layered earth. And then we did one for the cylinder, same thing. So you could look at the currents and the charges. We built pseudosections up, and then you notice that there's both 2 and 2.5D. So in the 2D, whenever you see that, whereas it really is solving a 2D problem. So that point source is actually really a line source. So that the potentials that you get out are actually significantly different than if you had a point source. On the other hand, the learning process and everything else is pretty much the same. The reason for doing 2D is that it's just computationally a lot faster. And when you're kind of working with things in a sort of illustrated that, you just want to get the result out quickly. And as long as that the same conclusion would hold if you did it more accurately, it just doesn't matter. So that's the difference between the 2D and the 2 and 2.5D. Then there's one that we're going to show you in a second. It's a plate. So it takes the same surface geometry, a homogeneous half space, and puts a plate into it. Okay, so actually, can you just go back to we'll just sort of run through. So then there was a number of EM apps that we had. We had the 2-coil one. So the purpose for that was just to try to get you to understand the whole business of coupling. And if I take a frequency domain source or time domain source, how the currents get partitioned into that inner coil. And then we looked at a sphere. The sphere could be buried in a 1D medium. Then there's also, that's fine, so I would just kind of go through these, right, just to kind of refresh your memory on how many apps we actually have. So looking at both the time domain with an inductive source and also with frequency domain with an inductive source. So there's quite a few things there. And then we went to the grounded dipole, and that's where we did all of the control source EM through the CSEM project. So that's in there. There's a couple on the in natural sources for MT. We saw those this morning. There's a GPR one that helps you with the attenuation. And then there's the inversion app. So of these, we're only going to look at 2 of them in the next half hour or so. The first will be the DC resistivity. And maybe the thing that we could explore here are just some aspects of Detectability, people are always interested in depth of penetration. And so then there's a question of, okay, can we see something or not? We did that a little bit with the cylinder app, but here we're going to do something that's a bit different. So we're going to have a half space, and currently we're listed between -40 and 40, so there's 80 meters across. So we have the usual A and B, so it's our current electrodes, potential electrodes are M and N, and then we've got a plate. It can have a resistivity rho 2 compared to rho 1 for the background, and it's got a thickness. So there's an X thickness, and there's also a length, Z, and then there's a location for the center, X and Z. So those are the parameters that could be played with. And so maybe it's, I don't know, of interest to just sort of explore this. So let's build a plate, let's build a model. Right? Much. Okay. Here, so let's just start with the default background here is 500 ohm meters. So let's just start with that for a second. So we got rho 1 is equal to that, and we're limited to -40 and 40 meters. So we got 80 meters across. We can go sort of 40 meters depth. So let's first of all build something that might be interesting, and then see if we can detect it. And then also we need to have some kind of a criterion for deciding, okay, is that significant signal or not? That would be the thing that you would be confronted with the depth of investigation. So let's first of all do that. So let's suppose we're going to have a plate of some sort. Let's first of all think how long would you like it? About a number.
2 kilometers.
No, it's 40 to 40.
8 meters is the total.
80 meters is the total, but
Yeah, 25 meters.
25 meters. Excellent. Okay, so we'll make it 25 meters. Okay. How thick?
3 meters.
3 meters. Okay. So 3 meters thick. And how deep should we put it?
What's the range that we know?
Well,
-40.
anything to 40.
Let's put in the bottom, 30 meters.
Okay. Got the guy, 30 meters.
We haven't set the resistivity.
Oh, okay.
Yeah.
Okay. Yeah, let's first of all figure out what this guy's going to be. It's going to be resistive. You want a resistive layer or conductive layer?
We can start with the resistive.
I mean, yes, it's hydrocarbons, right? We're looking for resistance. That's fine. This one's going to be really has to be more than 500, or else we'll change the background. What resistivity would you like? Pardon me?
No, I was
Oh, asking Sergio.
50.
50? Okay, so we're going to.
That's more conductive.
That would be a conductive. That's okay. Okay, so we've now got 25 meters wide, 3 meters thick, 30 meters depth. So first of all, without showing the apparent resistivity number, too late. So now there's a question of, okay, can we can we detect it? And importantly, can we detect it with whatever geometry we've got? So currently the geometry here, the A electrode was at 30, and the B was at 6 plus 30. So there's 60 meters here. Okay. So there's 60 meters, and we've got this kind of geometry. Maybe we could just look at the currents. That's usually the first thing that you'd want to do to see if we have the currents.
I'm running on binder. It's
Um,
probably.
Oh, there they are.
Yeah, that's fine. Take time to think.
So we've got this conductor in here. It's a factor of 10 more conductive. If we look at the primary currents, can we look at just the primary? There we go. Okay, so that's kind of what we expect, right? So currents just kind of go like this. Now we put this in, and now we can look at the total currents. It's taking fun.
It's running on.
It's actually running on the binder. We could.
Okay, that's fine.
Yeah.
Oh, that's okay. So this would give you some indication, like, okay, I'm distorting the currents, so that doesn't look too bad. I could actually take a look at the charges. Let's do that.
Total charge?
Yeah. Oh no, let's just look at secondary. Well, we can look at total charge. That's fine. So we already know what's going to happen with the total charge, right? So the total charge is basically, we've got a great big positive charge here and a great big negative charge there. So that dominates the eye. So now let's look at the secondary charge. And before we do that, what are you expecting to see for charge density?
Very weak response.
Pardon me?
Weak response.
But what about the charges? What?
Negative.
What? And where? Over here?
Right hands.
Negative.
Negative here?
Negative.
Yeah, positive.
Positive here, okay. What about?
I think you are at the limit of detection because the A-B separation is 60 meters.
Mm-hmm.
And the body is 30 meters depth.
Depth.
But if you use the rule of thumb of 1/3 of the distance,
Yeah.
it should be at 20 meters
Yeah.
to be detected.
That's a good point. So maybe we're not going
We're at the
to,
limit.
we're kind of getting to the limit. Okay, fair enough. We'll come back to that in just a second. So let's now just, first of all, think, are there going to be charges anyplace else on here or just at the ends?
Mostly at the end, but not, I think with a small decrease, not just in the end, because the field is not exactly horizontal. So if the field somehow tilted, maybe there's a charge not exactly at the end, but no.
Okay, and then what would we expect, let's say, on the top surface?
Yeah, but I think it will decrease as we approach the median point of the charge. Because if you look at we need to look. If you look at just the primary fields, yeah. So the currents, yeah. Yes.
That's a bit slow.
Yes, you think.
Okay, I think I might set it up.
Meters.
So you want to see the primary field?
Sorry, sorry.
Yeah, you need to-
Let's see, is it 30 minus 30?
Right. And what was the x?
And 5
25.
and 3.
So back to model. Okay, that was the model. Let's go back to primary. Okay, primary field.
Okay,
Yeah, they are almost horizontal.
almost
That's
horizontal,
why,
yeah.
So, yeah, predominantly the charts I think would be just at the end, maybe a little bit before.
And then if we were thinking about something at the top, what kind of a charge would we expect?
In the place that the field is going into the plate, it would be a small negative charge.
Yeah.
Maybe where the mouse is.
Yeah.
And on the other side, near the corner, a little bit of positive charge.
Sounds like a good guess. Let's try that.
It was just the secular charge. Yeah. Yeah, that's it.
Nice. Okay, so it's exactly what we should. We've got a concentration charge at the ends. There's a little bit of negative charge that's kind of bleeding around here, a bit of positive charge there. And the value of this charge is 6.9 times 10 to the 9. Times 10 to the minus. Good, okay. So we see that, and now there's a, if you're coming and ask for detectability, usually we have this rule of thumb that, 20, a third of this, so that's 20, 20 meters, it's very 30, so, are we going to see this thing or not? We kind of need a bit of a criterion for deciding, and so our background resistivity is 500 ohm meters, okay? This is a conductor, so kind of depends what your noise level is on the data, but if you thought of your criterion for maybe being like 5%, so so 5% on a DC resistivity is actually a pretty reasonable value. So that would mean 5%, so 25 ohm meters. So if you saw something like below 475, you start to think that maybe that could be it. So let's see how that works here. So let's go and see what the apparent resistivity is. And it turns out it's about that. So it's low, it's less than 500, right? And it's just kind of at that 5% difference. So this actually might not be too bad, especially if you had a number of data that were kind of showing this, and if you did a profile, you might think that was observed. But if you took the data and added 5% noise to it, you'd be pretty much on the threshold. Let's do two things. One, let's just raise. Well, actually, let's do. Maybe let's try. Let's first of all change it from a conductor to a resistor. Okay, so instead of being 50 ohm meters, let's go 10, factor of 10 the other way. We'll make it 5,000.
Okay.
Yeah, so now at 5,000, apparent resistivity is just a little bit more, it's 506. So that's going to be, perhaps not detectable. Okay, so let's take that and then let's see if we, and the total charge on that was 9 times 10 to the minus 10. So the total charge on that is actually a little bit larger than what we had for the conductive body, which is a little bit interesting.
And the way it's distributed, though,
Yeah.
is quite different. Wait, so what was it on the conductor?
It's 6.9.
6.9 times 10 to the minus 10.
Okay.
But you can see how, for this conductor, or for now for the resistor, there's actually negative charge that's.
I don't know where yours went.
Not sure what I did with my pointer. So the charge is actually pretty different. It's actually sort of positive here, and there's a bit of a negative that's coming up here. So the charge distribution has changed. The apparent resistivity is really not much different. But let's try bringing this thing up. Let's bring it up to, let's bring it up to 20, because that would be a third, right? Okay, so if we bring it up to 20, so that's helped us. We're 517. We're still not actually in that range of 5%, because we should be 520, 525. So this is interesting. We're kind of at that, maybe a detectability level. Let's bring it up another 10. Yeah, so now it's at, was it 10 meters depth? So now we're at 550. So now we're definitely seeing that. So let's just put it back down to, let's say 20. If we're at 20, we haven't hit our 5% level. But let's just see if we change the electrode configuration around, if it would make any difference. So let's suppose we put the B electrode over here by the A and made it more of a dipole. So we had minus 30. And then the M and the N close together over on the other side. Okay? So what's interesting here is that with the AB configuration over there, the total charge is actually reduced. It's down to 10 to the minus 11, but the charge distribution has changed substantially. And look at the apparent resistivity is now 600. So now it's 20% more than than what that background is. So, I mean, I think the impact point here is like, okay, we've got kind of a rule of thumb of, we can basically see a third of the depth, but that's only some kind of an approximation. It's going to depend upon whether the object is resistive or conductive, and it's also going to depend upon what your relative configurations are of your transmitters and your receivers. The other thing, so here it's 616, so we're definitely seeing this guy at this point. Let's do two things. Let's make it conductive. We'll go back to so. And now here in this particular configuration, so at 474, that's just at the 5% level from before, right? So, things are kind of moving around a little bit. If we bring this one up, let's bring this up to more towards the top. let's bring it down to, so it's -10. What happened to the... Change your colors here.
Yeah, it's not centered about 0, which is a bit confusing. So you'll notice that the blue
Yeah.
Goes to -8 times 10 to the negative 12, and the red is now at 3.
Okay.
So right now, unfortunately, white is not 0.
I see. So sitting up here, we're at 580 ohms, so we're well above that that threshold. If we just made it shorter, so if we decrease the length of it, then what would you expect to happen?
Or what's the parameter that you're...
Now what? So we've got this 25 meters length. Okay. So now we're trying to find this guy here. No problem. We can see that at 25 meters.
Yeah.
What happens if we shorten it?
Yeah. I guess the apparent resistance will be closer to the 500 background resistance.
Let's see. Let's just make it 10 meters instead of 25. Yeah. So now you're making your target smaller. So when people say, well, how deep can I see? Well, that depends what you're looking for. You can see a certain length or a certain size of target, a certain resistivity of target at a particular depth, but it's not really a very easy question to answer, but you can get an idea of, by using an app like this, of how much difference you would expect, and then to factor that into, okay, what's the uncertainty in the data? How noisy are the data that I'm going to?
In actual feasibility studies, you just look at this as we are doing right now, or would you actually do all the geometry, invert, the model, let's say 20 meters, now invert, see if we find, like now 25, do the sounding, and you do all the modeling inversions to see if we're actually going to see. Because we're just looking at the apparent resistance, but the points that will at the end answer.
Right. Yeah.
The inversion will provide us with that. Right?
So I guess the first thing is that I would experiment a little bit with this just to see, because I might want to decide whether I use a pole, dipole, or what kinds
of what
kinds of signals I would expect. Do I have a chance, right? And then I know if it looks like I have a chance, then I'd actually lay out a survey, which would be a pole dipole or a dipole. I'd get that pseudo section, and I'd compare that pseudo section with the target and without. Okay, so can I see something in the data? And then the final step is that you really actually want to perhaps add some noise that is representative, and then go ahead and invert the data. Or at least, even if you're going to invert synthetic data, you don't necessarily actually have to add the noise, but at least assign those levels of noise that are appropriate, and then go ahead and invert, and then see what you get. So that would be the sequence of steps. Okay, so I think that's good. So let's just open up the inversion app. First of all, did anybody kind of experiment with it? Have a look at it? It's because you guys were all saying, "Oh no, I know, I saw you there."
Yeah,
and you were drinking.
I was about to say that.
You were drinking beer. Yeah.
We all were.
And you decided.
You were there.
So. Yeah, but I didn't. Nobody assigned me the problem of having to go and work this out. That was your assignment. I was just told to go and drink the beer. Okay. So just to kind of refresh your memories, we've got things set up so that you can have linear data with kernel functions. those kernel functions are decaying and oscillating. And so depending upon your circumstance, you could try to experiment with different numbers of data, different wavelengths, different rates of attenuation, and see what you get out. So the procedure will be to decide, first of all, decide on our model. Okay, so what is that going to be? So let's first of all make a model. This is one that's going to be your default. If you like that, we can live with that. If you want to try something different, now's the time to say we can alter the center point for the Gaussian. We place along here, the center point for the boxcar, and we can change the amplitude and the clarity.
I think it would be good to put at least one in the opposite polarity.
Which one?
Which one?
One. The first one, the square.
Yeah, okay, so let's put the square. Yeah, how about that? So we've got low velocity zone and something that's higher.
Is it possible to choose the kernel function also?
To some extent. And there's actually a fair bit of flexibility because we have control over how rapidly they decay. We have control over the numbers, and we have control over their frequencies. So maybe something that's more connected with the seismic problems is that you really have wavelets that are highly oscillatory, and then I think do your general seismic wavelets tend to they have zero area, right? You don't have any. You don't have any net area under the curve. You're missing all of the DC, very low frequency information. Is that certainly by the time you've done the data processing, you've lost all of that low frequency information. So your seismic wavelet, right? Is if you did the Fourier transform of that, you'd have zero in the DC. Yeah. Right.
Yes.
In the source, we don't have this low frequency. In the recording instrument, we can't record this low frequency. In the processing, we do. So
yeah. So basically,
whatever reason, we don't. At the end, we don't have it.
Right. So we could try to emulate something that's similar to that. That means that we're not going to start with a frequency, like we don't want to start with a zero frequency. That would just be a kernel that's a constant across. So all of our frequencies are going to be very oscillatory. So we could try that. Let's see. Yeah, and then let us. No, that's okay. Let's start from J. Can we go J something higher? 5. Does that do it? Yeah. So here's a set of kernel functions. So quick. I gotta figure out how to turn that off one of these days. But so far, it's just making sure I'm awake. And there we go. Okay, so here, look at the blue line. So it starts here, goes up, now up. So if it's not zero area under there, it's probably pretty close. So those are our kernel functions. Each datum that we have. So now let's go back and look at the data. So each datum that we have is that inner product of this model with these kernel functions. So here's what the final data look like. So let's plot the kernels too. Here's our kernel functions. There's the model, and here's the data. Okay. So now let's add just a little bit of noise to those data. Something that looks like that. And now that's where we are. So here's our data. We know what the kernel functions are. We want to recover this guy. So let's first of all start by not having any regularization function. We're just going to worry about fitting the data. So we'll make these. Remember those? There was two alpha coefficients. One that pre-multiplied the smallest model component, or the energy, and then the other that pre-multiplied the penalty on the derivative of the model. So now, if we just are going to, so let's put max at 30 iterations max. And we just go ahead and invert that. So we're going to start here at the first iteration. So we're starting off with a reference model that is 0. So we're starting off with a 0 model. And then as iterations continue, we'll see, okay, so now we're starting to see a little bit of structure, and notice that we still have a really high misfit. So we're starting to get, notice right in here, we're starting to kind of fit these big amplitude data. Let's go a bit more. Another one. So we can see that we're kind of coming in there. The model is still pretty oscillatory. Let's keep going. So we're kind of doing okay. Actually, just go one previous. One more. I thought we kind of put a step up there. Okay, maybe that's fine. So we kind of have something there, but almost this is just like a harmonic function. But we are getting close to fitting the data. And now let's just continue on. Going. So you can see as we fit the data better and better, we end up with just a lot more structure. Keep going. And I guess that's going to be kind of where things are going to stall out. But you've got something here that really doesn't have a lot of good resemblance to what it is you're looking at. So now let's do two things. Let's go back and just try to add a little bit of smallness to it. And then we'll also, maybe let's just try one for that, and we'll see how that goes, and then we'll add some smoothness. Go ahead.
Do you want smoothness?
Oh, yeah. We'll just,
Can you, alpha x should be 0, so.
okay, so let's see where this takes us. Kernel functions are a bit harder maybe than we usually use. Okay, keep going. So now have we helped ourselves very much? Maybe not very much. Okay, let's try adding some smoothness to things. So let's put 1 in there and see how that works.
I think we probably added too much noise, I guess.
Yeah, I'm not sure what.
The floor was actually pretty big.
Do you want to show a case where we change
Yeah, where's this guy? Whoops, what happened there, buddy?
I think the noise is way too big here. The floor is pretty big. That's my guess. I think the starting point was like that. Your misfit was pretty small.
Yeah, okay. Yeah, so let's,
Your floor is like 10% of your data right now.
So floor is just too big.
yeah, so let's go back and add a lot less noise.
1.05, a little bit smaller. Yeah.
Yeah, that was the same. You want to walk through or?
So alpha S here is very small again, so we're
Oh,
basically not
I
using
see.
regularization.
Oh, okay, I see, we're back to kind of starting at square one. So this is what's going to happen if you just fit the data really well. Yeah, keep going. Okay, so that kind of brings us back. There's some element in there that's it's got some kind of character, but it's surely not anything like that. So now let's go back and use some regularization. Put one in there too. See what that does. So this would be your default. See how that works.
I think that.
Somehow the fact that we've got like the negative in here and a positive is kind of there's sort of a resonance with these kernel functions, right? That seem to kind of drive us back to something that we're constantly. Anyway, let's see where it goes.
Well, because it's probably not far in frequency from some of the lowest frequency.
Yeah,
kernels
exactly.
that we're looking at.
Exactly.
So you're probably almost like we're just basically recovering those lowest frequencies.
Yeah, the first couple of harmonics.
Yeah.
Can we decrease the alpha S? Or just keep going?
Yeah, let's keep going. Let's just see where it goes. Okay, let's go back and just change our kernels. And sometimes if you have a poorly designed problem, you're hooped. So let's just go back to what we'd ordinarily.
But even just before you do that, like looking at those lowest frequency kernels, that really is very reflective of the lowest frequency we're recovering in our data, right?
So this is a linear program, so it's a little bit the linear combination of kernels. That's why.
Yeah.
That's why it's so oscillatory.
Yeah, exactly.
Little you can do. Take this kernel, right?
Okay, so let's go back and go. J is equal to. Can we use J is equal to 0? Or at least J is equal to 1.
We can use 0 if you want.
So then that'll give us the constant kernel. Yeah, so now we've got these as data. Okay, so in this case now we don't have any regularization, so we're back to this. Okay, so let's see what that does. Okay, so here now so if we've got kernel functions that sort of span the active space in model, so here's actually a pretty good representation of what we have. And now keep going. So we've got quite a bit of extra structure there that we wouldn't ordinarily want. So let's just go back to putting on a regularization and also looking at an appropriate misfit. So let's just go back, put 1, 1, just our default. So this was the target misfit, so that at this point here, it's fitting to about what we would have thought. So someplace in this region here is probably going to be a good place to stop the inversion. And then just keep going. Yeah, so again, now the same thing. If you have a regularization, if you overfit, then you're going to be good. Yes, maybe we could just explore one more thing, and maybe that's with the reference model. So let's change the reference model, which was currently at 0. Let us change that to, let's try -1 and also take off the smallest model.
Take off?
No. Leave the smallest model and take off the
smoothness?
flattest model. So now what we're doing is trying to make something that's as close as possible to -1 everywhere. So it's not going to be able to do that because the data are going to, some of these kernel functions have information at late times. So we're not going to be able to make it -1, but I mean, we could try to see how well we can do. So there's our reference model. So we're actually, for some reason or other, we've guessed incorrectly. We think, oh, everything should be -1. So now we're going to do this experiment, try to make something that's close to this, and we'll see how well we can do. That's the target misfit. So again, the data, even though you try to have something that was close to -1, the data are powerful enough in this case that it overrides that. So that's good. It means your experiment is.
But in this case, you had all this lower frequency data.
Yeah.
Right?
Yeah, so now we can try getting rid of some of the, maybe just
Go back.
go back to J being, let's say,
Yes.
2 or 3. Yeah, 2 or 3. Okay. Okay, so now we'll MREF is -1. And then let's yeah, alpha S be 1. And we make alpha X equal to 0. That's the same as we had run before. Okay, see what happens there. So it's going to start off with everything at -1.
Yeah.
And
It's
now
a bit harder to
it's going to be really,
shift.
it's going to be really hard to shift up.
Yeah, because we don't have this low frequency.
You don't have that low frequency. That's what you're commonly affected with.
Yeah, that's exactly the same in size. We need to grab those low frequencies from different information source like wells, and then we add them as this background because we don't have them.
Right.
Experiment. Yeah. That's exactly the same.
Yeah. So I mean, as far as fitting those data,
you recover the high frequency aspect. If you look at this blue to the red ones,
down, up, down.
Almost this shift that we miss. That's nice.
Okay. Anyway, so there's lots of parameters to play around with, and just get a sense of how important certain things are. And we'll be developing more, kind of examples and 2D as well as 1D, and allow it to get a better sense of what's going on. Okay, so why do we have, if there's no more questions, or did you want to hand out can we get you to do one thing before we actually break up?
Or during the coffee break.
Or during the coffee break?
These are feedback forms. These are very valuable for us just to get information on what they worked, what didn't, what we should do in the future.
Okay.
So we appreciate it.
Thank you.
Aqui na cena, o médico lá, chegar, olhar, olhei só um pouquinho, não vi o que era mesmo, vou olhar de novo, mas, cara, o cara só chega lá e
Acho que ele esbarrou com o Nicolás sem querer, o Nicolás perguntou alguma coisa, ele só não dizer nada, ele disse isso.
Ele foi o pessoal que não do meio médico.
Mas o cara tá dando tempo para ver se o seguro é quente, né? Pra saber como é que vai tratar o cara. Quando já tá bem.
Claro, né? Dizer, ó, vou sair disso aqui, mas para seguir com o tratamento eu preciso dar fazer o seguro, não sei outra coisa. A primeira vez que o cara falou que era um intervalo, ele não contou assim nada aí.
É o último, né? Que é só que chegou aqui.
Was it 2 months? Over 2 months? Yeah. I contacted Weena, tell her that before 30.
Uma animada que fica cara de
Did you find that laser pointer?
Yeah.
Yeah.
Yeah, we have 2 here.
Excellent.
So we're in good shape. Yeah, absolutely. Just might have a bit of coffee. Oh, we should contact Edwin and tell her it'll be closer to 4:30.
Okay, I'll text you.
Because
Yeah, that would be.
that's okay. Can make it through 45. Everybody's vacating. It's just too much. There's too many new things. Yeah. That's okay. Yeah, having really good pre-programming examples. Getting lost by right.
Is just
I just want stuff out. Yeah. And then yeah. These shows are not unique.
Well, and shows the importance of that DC and low frequency component, so that's good.
We should see if we can find Korean. Fusion.
Yes. So you what was the name of that food truck that Adrena was telling us about yesterday?
Oh.
Something go G.
Oh, I think Goji, oh my Goji.
Oh my Koji, right? Oh, it's probably only open for lunch. Often food trucks do that.
Really?
Yeah. Oh no, wait. Yeah. Oh, it opens at 9 p.m. I see. 9 p.m. till 3 a.m. That seems strange.
Seems a bit long. What was this? This Koreanus? Is that?
No, oh my Goji.
Oh my Goji. There's faux Jita fusion. We don't want healthy food trucks.
Of course not. What time do you want to resume? If we tell everybody to be back at 4, 10 minutes?
Oh, yeah.
Just
Just get up, stretch your legs, grab a cup of coffee. I think people are about done. We're done.
I just texted her doing it and told her maybe closer to 1:30.
Yeah, so that's perfect. It'll take us time to clean up.
But I think they want to say goodbye to all the students.
Has anybody heard anything from Luis? Update?
Yeah, he done the X-ray exam,
Yeah,
so it's confirmed that he broke the bone.
yeah.
And now the doctor is still deciding what's the
Next.
best next step. So we're still waiting for the decision.
Well, progress. I mean, now you know what you're up against.
Yeah.
That's always the biggest.
So very unlucky. We are here for about 2 months, 9 weeks. So it's quite ironic. The last day, the last one day before we had our first.
You ready for weekend?
Yeah.
It's okay.
Well, that happens also in sporting events, like if you're out skiing or something, then it's that last run. You're like, oh, I gotta do one more run, right? And then your legs are tired and whatever happens.
Well, as long as not the first meeting, it wrecks everything.
Yeah.
I guess it always is the last one. So that's so quick.
So it's the SCG. Last year it was like 2 or 3 weeks after the flooding.
So all my colleagues checking his house to see if there's any leaks. So he went to the RA, and then he kind of fell down. So he broke his I think also arm. And because it was flooding, so like the ambulance cannot get close to the house.
Yeah.
It was like really hard to do.
So because you got a currents are now it's like electrical dipole, right? So you're gonna get some positive peak and also you get negative. So it's like
This is just a direction. The direction.
no, this is just a white.
So the negative meaning it's in a negative y direction.
Yeah.
Okay.
So yeah.
It's the game, card game. Dutch blitz.
He's very green, very tight.
He's something.
Get everybody moving.
Yeah.
How do you manage to do all these subjects in one day?
Good question. We have no idea. And thinking about it, we have no idea.
So, yeah, one of the points that I mentioned here, it would be great to have, let's say, a time to try the apps
Yeah,
in the room.
more time.
But then I was thinking, oh my God, they do this in one day. So,
Well, there was only two or three places that we were forced to do it in one day. Most places we did it in a day and a half.
Which is still fast.
There was not really an opportunity for people to interact with the apps. Because then the other half of the second day, we heard from participants as to what they do. So it was a lab day. So you would tell us what you were doing and capture that. But yeah, after having, well, we always felt like we were really short of time. And so that's when the opportunity came up to do this in Houston, we thought, oh, that's a pretty good idea. Let's just try it out and see what it would be like to take that material, add a little bit of stuff, and make it a week-long course. And even at this, there's a lot of material, and it's hard. I think especially when you don't know a lot of stuff, there's just so many new terms and jargon and stuff that's coming in. It's challenging.
All these points that you were discussing, do you actually do research in every of these points, or you're just like sharing? Okay, this is all the subject that we have in magnets, but do you actually work more specific in one of them, or this you work
everything except the GPR that we worked on? Not necessarily at the same scale. Like, I mean, we've certainly done magnetic tellurics in 3D, but not at at that Red Sea level, or also with the marine CSEM. We haven't really done very much there, but we've definitely worked with all of those different types, frequency domain, time domain, airborne, ground, DC resistivity, IP, all of those we have done. Encased wells.
Yeah, it's been nice having this be a week. It's nice to have time to go into things more. So I think for the day and a half, like just the expectation was different for what people would get out of it. It was much more like a once over, you see everything, but you just don't have time to really get into it.
So what did you do your master's thesis? You said it was in quantum mechanics, right?
Yeah, I studied physics as a background.
Yeah.
And I studied in theoretical physics for quite a period. And then I was actually teaching physics. I trained the Brazilian team that participates in physics Olympics competition studies.
Oh, yeah.
Yeah, it's very.
Oh, that would be interesting.
Yeah, that's very, very nice too. So
Wow, you
like
have that
5,
collection
6
of really bright young people that you're working with?
Yeah, we train like there's this International Physics Olympiad. So it's every year, so each country sends like 5 students, but students, high school students, like 17 years. So you can think like 16, 17 guys that has the knowledge like all the calculus, all the things that they are not supposed to learn by this age, and strong physics intuitions are nice to see. So I moved from this theoretical physics to this training.
Oh, what fun.
I was much involved in this competition. By the time I was a student, so I just keep going.
So how did your students do?
Yeah.
Okay.
We started by when I was a student, we were like I don't know how to say in English. I say cobaia.
Red lab.
Yeah, I don't know. Yeah, I don't know the expression in English, but when I was a student, we were in the first group of Brazilian students. And that went to represent Brazil in this international competition.
Oh.
So, but by that time, for the time that like 5 to 10 years then, Brazil also get this almost in the top level of students. So we are achieving like silver to gold medals in this Olympics by now.
That's great.
So it's and then I changed everything to go to the ion industry.
Are you still connected with that program?
A little bit. Still connect. Sometimes I go to talk to them for a week, but now it's another goal.
Yeah.
Eles vão de Olimpíadas,
Soltar. Olimpíada de Física?
Okay, do we have a quorum? So it's been it's been 5 days. We're about ready to wrap up. I want to just kind of do a quick summary of where we've been and where we might go. So. So when we first started here, I put up a slide talking about roadblocks with respect to the use of electromagnetics. And things that I said was that people generally don't realize the role that EM can play in solving a problem, don't understand the technique, using technology, seems complicated, unintuitive. What's the question between my problem and the physical properties? And there's just so many types of surveys: DC resistivity, frequency, time. Where should they be? On the surface, in the air, downhole. What do I expect to resolution? And are there situations that are similar to mine? So those were kind of the motivating things that we identified, and we've been spending the last few days trying to kind of parse through all of these things and see what, see if we can't overcome those roadblocks.
As a roadblock, you should put bosses as well.
Bosses?
Yes.
Good point.
Geologist bosses. Geologists. Yeah.
I think the really positive thing, this is why we're so enthusiastic about electromagnetics, is that there's just so many problems out there, and that electromagnetics can play a role. And it hasn't played that role up to now, primarily because there wasn't adequate data that were being collected. Data that were collected were not properly interpreted. You've got a three-dimensional situation. You try to invert in 1D, the chances of you being wrong are pretty high. But we've turned a lot of those corners, and we now can collect better data. We know how to handle the problem. And so I think there's an opportunity here to really start to do a lot better. What we tried to do was to really look at all of the really important aspects here. I think this is perhaps one of the few courses that really does that. We go right from DC resistivity, looking at the fundamentals. We look at inductive sources, grounded, natural, some aspect of inversion, GPR, induced polarization. So I think when you have when you have a problem and now you're asking, okay, can electromagnetics be of use? The fact that you've got all of these ground pieces means that, okay, yeah, it might be used here, and this is kind of the technique that I want to do. So whether you need a natural source, or whether you could have a some kind of a grounded or inductive source, you'd have a better idea of what might be feasible and what to get out. We started off with DC resistivity. We've seen all of this a zillion times, but the important things here are just the general physical properties of this, driving current into the ground and getting charges on bodies, and then measuring potentials. And we've looked at the charges, at the currents, pseudosections, and how to plot them, and talked about different soundings and arrays. Survey design, mentioned briefly, and then a couple of case histories that have to do with monitoring, also with mineral exploration. And we talked about the important aspect of shielding. DC resistivity looks good, but then there's cases where, it's just shielding the target. And that meant that we need to go to electromagnetics. And for that, we had to look at the fundamentals of EM. Time-varying magnetic field generates currents in conductors. Important things about coupling, not only coupling of the transmitter with the target, but then coupling the currents in here, the fields with a receiver. So there's always two sets of couplings. We looked at the characteristic response curve for frequency domain EM problems. And importantly, we saw that understanding everything, you could work either in the time or frequency domain, but it's easier to understand things in the time domain, and you could see how currents are flowing as a function of time. And physical principles in the frequency domain are exactly the same. It's just that the current can get delayed a little bit. So there's a current and then there's a phase shift. And then we could write that equally as a real and imaginary part. So that's all that's happening. And then in time domain, we had a diffusion distance that we were concerned with. So that was basically kind of telling us about how far the peak of an magnetic impulse would make it into the Earth after a certain length of time. It depends upon the conductivity in the time. And in the time or in the frequency domain, we had this decay, and then we had the concept of scan depth. For the EM fundamentals, everything kind of boiled down to the fact that if we ever manage to put a current into the ground, that current is going to diffuse downwards and outwards and gradually decay away. And so we looked at that phenomena. And we also looked at the effect of background conductivity, because we've got to get energy from the transmitter to the target, and our ability to do that now depends upon what that background conductivity is. Oops. Oh, back here. Okay. We looked at inductive sources, mainly a vertical magnetic dipole, so horizontal loop, vertical magnetic dipole, and we also looked at the horizontal magnetic dipole, so you turn the loop on its side. Case histories, casted, that was looking for the top of a clay layer and then trying to see how deep the valleys were that might have aquifers, and then tried to use that to get a hydrogeologic model. Lalor, a deep buried conductor. We used a surface loop and airborne measurements. And then Wadi Saba, where they used a time domain EM to get near surface structure, and that would then help with their seismic velocities. With respect to the shielding problem, we also looked at both frequency and time domain and showed that if you have a resistor, there's no harm in that at all. An inductive source sees right through that resistor. If it happens to be a conductive layer, then you might still be shielded. In the frequency domain, we looked at an example in Australia, a Bupernov that had saltwater intrusion, and then also in Dom Joao. Close. Two.
That's good.
Okay, so looking at steep floods and seeing if we could drive fluids into upper couple of zones that had hydrocarbons in. And then West Plains, this was a mineral deposit. The reason we showed that was that it was airborne, both time and frequency domain data over deposits here. And we also showed there that you could do like a parametric inversion to try to find a few parameters and then use that to help start a voxel inversion. And then logging while drilling, that I think that's something that might you'll see more of. So there's different orientations of the coils. And so as that's turning around, now you're illuminating this way, this way, this way, this way. That gives more information, and that could be used to determine where the upper and lower boundaries are and steer the well, or to find out how thick that pay zone is. Grounded sources, we combine what we had from the two previous surveys. So we got sort of DC resistivity, and we also have a wire that's giving out time varying magnetic fields. So you get both induction, you get induced currents, vortex currents, as well as galvanic currents that come through. There's an electric dipole app that we provided that you can look at. And examples that we did were the Deccan traps in India, as well as the marine CSCM. Barents Sea for de-risking, and gas hydrates in the hydrate ridge. That was pretty much the controlled sources. From there, we realized that, okay, we need to have more energy that comes in. So we could get that by having basically plane wave sources, so they don't have that geometric decay. So they still lose energy because of attenuation, but they don't have a geometric decay. And that can allow us to see to greater depths. Z10 we didn't talk very much about, but that's that Tipper experiment where we measure the vertical component of the magnetic field as we go across and use the ratio of that to a horizontal magnetic field at a base station. So that's a great geologic mapper, and that might promote at least potential for looking at Tipper data for your example that you had earlier. We've got resistive structures that are buried at depth. I mean, there's a possibility there. For magnetotellurics, the data are the impedance, and we could convert those to an apparent resistivity and phase. We showed a geothermal example from Henkett and walked briefly through a porphyry deposit, Santa Cecilia, where we use both DC resistivity, control source, MT, as well as MT. So those three things each provided its own conductivity structure, and we were able to see that with the MT you could see deeper, and but yet in the places where you're closer to the surface, all three provided consistent results. Hydrocarbon example from Daniela Colombo in the Red Sea, combined CSEM and MT into a section where we got a much better idea of what the complex structure was in the upper regions where you had clastics and halite, trying to unravel that so you could get a better velocity model and hence a better seismic section. On inversion, we tried to provide the basic understanding of the inverse problem, as well as how it's set up, and the importance of incorporating some kind of regularization, talking about non-uniqueness. There's links there to SIMPEG, and there's a lot of tutorial information as well as examples that exists on the SIMPEG site. So hopefully this will open up a window for you to explore more what's there and to use it. The important thing here for the inverse problem was really kind of defining two quantities, the misfit and some kind of regularization or model norm, and then trying to make an appropriate balance. Also talked about forward modeling and inversion of kinds of things that we're dealing with in electromagnetics. We didn't go through the mathematical details, but you got enough to kind of get a sense of like, okay, what are you really up against? And you see that for the time domain work that we've been working with, you still need to solve the forward problem, many millions of times, and that kind of sets a benchmark for what you need to have for computing facilities. This morning we looked at ground penetrating radar. No similarity between that and seismic sections. So this section here could be seismic section, turns out to be GPR section, but it's the fact that it's sort of wave propagation, that you've got a pulse or some kind of a waveform that's going down, reflecting back in, makes those two things the same. And we showed an example for potential use in driverless cars as sort of extra piece of sensory information. And then induced polarization, we just went through that this morning, looking at sort of a cartoon representation of how to think about the problem so that you could have a visualization of how charges would be built up when you apply an electric force and how they then dissipate. And then how to invert IP data. You always need to have two, it's sort of a two-stage process. One, to find the electrical conductivity, and then the second stage is to use the polarization as sort of a perturbation on that and find the chargeability. And our example that we used was the Mount Isa, which we've done at the beginning with DC resistivity, and now we do it with chargeability. So that's pretty much what we've done on a brief walkthrough. Question is, what does the future hold? I don't want to elaborate, but just kind of comment on a few things. This is the important one. It's now a margarita, and that's made with silver. Is it?
That's what we were told.
We're told the silver.
Silver.
It's important. We can go now. Just a few comments. So GeoSci is trying to kind of connect all of these things, problems, high quality data, version capabilities, web tools to communicate. Future, not only within the hydrocarbon industry, but elsewhere too. If you look at electromagnetics, there's all kinds of places that EM can play a role. Dam integrity, that's a big one, not only for tailings dams, but also for earthen dams that's holding in water, slope stability, monitoring aquifers, coal seam gas, enhanced oil recovery. All of these things require that areas be instrumented and that you look at changes over time. So many of them are time-lapse things, hence the monitoring. Choosing an appropriate survey is important. I thought I might have a couple of slides on this because it might resonate with you. In Alberta, we've been interacting with companies that are doing SAG-D. And so in SAG-D, as you said, we have a steam, we've got two vertically parallel pipes, one of which is a steam injector and the other is a recovery one. And so we put the steam in, it lowers the viscosity of the oil, falls down, and it's channeled through a collecting pipe. So if you're going to build one of these, then there can be multiple stages that you really want to use electromagnetics. And the first stage might just be a reconnaissance survey to try to figure out, okay, what is that background connectivity? Because the ultimate stage in monitoring, what you want to know is, okay, where is that steam, and yeah, what is its state? There's been a couple of allusions to that here, that you're pumping in steam, or you're pumping in fresh water or anything else, and you don't really know where it goes sometimes. So if you could monitor that, then that would be great. So I'm going to show you just some synthetic examples of potential use of different types of surveys to ask different questions within the context of this whole problem. And the first stage is reconnaissance. The next stage might use some surface and borehole, and then the third is monitoring. This was kind of interesting. So again, this is in Alberta, and there's a formation that's called the McMurray Formation, and this is the hydrocarbon area. So this is what you're really trying to mine, and you're trying to find out where it is. And above this McMurray zone, there is a conductive clay cap that causes. I mean, the good news is it prevents oil from going up, but it also is as a conductor, and you need to know where that is. From the oil company's perspective, what they wanted to do was to know what the top of this McMurray zone was here. And two things are presented in here. First of all, they did a lot of drilling. So each dot on here is a borehole. Each dot is a borehole. So that was drilled into here, and then they got the tops of that formation and then plotted it up. And that's what this diagram here is. It's this is an elevation above sea level of where the top of that McMurray is. The airborne data was run over here, time domain data, and those data were then inverted to recover a conductivity structure. And what we see here are the results of that at 3 lines across here. And then those were interpreted to find what the top of this McMurray zone was. And when you do that, you get this image here. So here's the image of the top of that McMurray that's obtained from airborne data. And here's the one that's obtained from all of those boreholes. And you can see that there's a remarkably good similarity there. So when the oil company actually saw this, they were actually pretty impressed with the first order information that could be obtained just by doing a single airborne survey here compared to all of those things. The next stage would be for monitoring. So now assume that you've got this region and you're going to have some horizontal wells, and you're going to put some steam into them. Okay. And this is a simulation of that. So these are basically 3 SAGD chambers that have been generated, and steam has been injected. In this one, and the 2 outside ones, the steam has gone right up to the surface, and in this middle one, there's been a spot where the steam has not been able to penetrate. So there's a bit of a blockage zone. If you do a cross section through here, then this is what it looks in cross section. So there's steam that's gone right up to the top on the outer 2. So the goal is to try to see if you could image what those steam chambers are. So in this case, what was done is to have borehole receivers. So these are just electric field receivers, just the kinds that we've been talking about in these boreholes. And those aren't extra boreholes that are required. Those boreholes are mandated to be there. They're observation wells that are required by the government. So it doesn't cost any extra money to do that. And at the surface, we've used a large loop, two large loop time domain surveys. So by having a surface loop transmitter and borehole receivers, we're able to get out electromagnetic data. Those are inverted and they give an image that looks like this. So we can see from surface data now, from surface sources, these steam chambers, and also you see that region of blockage. So that looks pretty encouraging. I think the oil companies involved are actually extremely excited about this, because this stuff is at a depth that is kind of hard to work with seismically. It's in the top, 300, 400 meters, and now you're talking time as the seismic experiments are very expensive, whereas you could manage to do monitoring time domain experiments actually fairly inexpensively and do them quite regularly. So you reach it, electromagnetics, if you see, as you go down deeper, has poorer and poorer resolution. And down deep enough, then there's no comparison with seismic. But if you start to take the structure that you're interested in, and as you bring that up closer to the surface, that as it gets up closer, actually electromagnetic techniques start to have some advantages compared to the seismic. So it's kind of trying to figure out, okay, where is that sweet spot between using seismic and the EM, and probably ultimately you want to use both of them, but making sure that you're using them responsibly and cost effectively is important. Other challenges, we're starting to see a lot of work being done on casings and looking at what the effects of casings are. I talked earlier about using these steel-cased wells as extended electrodes. So for instance, if we've got a hydrocarbon target that's sitting out here, if we hook a current electrode up to this well, then energy will be sort of funneled down into depth. And we can actually excite this target much easier than if we had been at the surface. So there's an advantage for steel-cased wells there. If you're actually going to start working with these numerically, then there's some pretty significant challenges, because the geometry is tough, right? Because you've got 10 centimeters for the diameter of the casing. The outside of the casing is steel, so it's highly conductive. The length of the well can be long, kilometers. So from a geometric position, you've got modeling of centimeters here, as well as many kilometers. So that change in scale is challenging. Also, the change in conductivity contrast is challenging, because the outside here might be sort of an ohm meter. This is a conductivity of 10 to the 6th Siemens per meter. And that's 6 or 7 orders of magnitude different. So that makes things numerically challenging. The other thing that people are worried about, we talked to Glenn Wilson of Halliburton here just a couple nights ago, and we're asking him how many wells there are in North America. And what would your guess be? How many wells do you think they have in North America? North America, yeah.
In the US and Canada?
US and Canada, yeah.
Only on land?
Yeah, just on that.
50,000.
Oh, it's much more. Okay, I remember that Only in the Illinois basin, it was, 100,000.
Millions.
That's Chevron. Yeah, the number you said, 9 million. 9 million wells in North America. That's a lot, right? And then now you go worldwide.
There's wells, if you think of oil production in Brazil, maybe one well in our pre-salt, the same production of 4,000 wells in onshore northeast of Brazil. So the number doesn't tell.
So, well, yeah, that's true. So the production doesn't necessarily raise the number of wells. But the point is, there's a lot of wells.
Yeah,
And
that's a lot.
well integrity is a big issue. Right? So wells are made of steel. Steel has a high permeability. Wells can erode. Up until this point, we've just been talking about things being electrically conductive. But once you're talking about steel, then you've got magnetic permeability. That could be a factor, that's 100. And so that needs to be taken into account. So there's lots of challenges, and actually looking at well integrity is a big issue. You've got 9 million wells here. When some of those fail, then they cause problems. So I think there's a lot of challenges here for the future with respect to, numerical modeling and implementation, and just trying to get more information out about, where reservoirs, there still might be some oil in an oil field that you haven't really tapped out. You want to try to find that, extract it, or just keep everything that you're working with now as far as the wells, making sure that they're good integrity. Yeah, and again, in the future, there's higher quality data. We've continue to have improved instrumentation, low noise, more power, and then details with respect to the waveforms that are going in, and filtering parameters, and just keeping track of everything. As you get better and better with knowing all of the details about the survey, where the transmitters and receivers are, and all the orientations, and tilts, and all the other things, you can actually extract more information. So that's the goal. And now what we have as big data comes along, especially with drones and AUVs and ROVs, we're starting to get to the point where, again, the electromagnetic techniques now can be more and more important in that overall problem. So just the same as I'm sure people in the seismic industry are saying, like, okay, we've got big data, we need to somehow put all of these together in multi-physics and machine learning types of environment. I mean, that's definitely where the future is going. And then, real-time inversions, as I was talking to you before, this logging well drilling, having these sensors that are oriented differently and capturing the data in real time and being able to invert them in 3D and figure out where that drill is with respect to the upper and lower horizons. Those things are coming on stream and will make a difference. Yeah, marine EM, I think there's a huge potential there. We talked a bit about gas hydrates. There's also seafloor massive sulfides. So you have these ocean ridges, right? So the minerals, water gets circulated through here, minerals come up, and then they get deposited on the ocean floor. What they're now looking at is the potential for just mining these. So you just come off with a great big ship, and you put down sort of coring devices or mining devices on the floor, and they just chomp things up in a swath and funnel it back up to the ship. These are very highly concentrated ores, and you could then take them back to shore and have them mined. I think we're going to see a lot more of that. There's ethical questions that are going to be involved with respect to harming the marine environment, but minerals are going to be required in the future, and they're costly to do on land, and there's certainly environmental consequences on land. So trade-offs people have to think, but the technology for doing this now exists. And in fact, that you can have deep sea ROVs that are collecting the EM data, inverted in 3D, means that this will happen. And the Japanese will be mining this next year. And then there's also large-scale tectonic hazards. You get subduction zones. You want to know where those are, so areas of weakness, and maybe stuff connected with anisotropy to just help unravel the complexities of what's going on. Yeah, and there's also some really large-scale problems that are being done. So this is Australia. We talked about magnetotellurics. These are all the MT stations that either exist or are planned for Australia. So they're planning to cover the complete continent with these MT stations. In the United States, these dots indicate empty state.
Those are permanent stations?
No, they've been put out in arrays, so they would put out a number of stations, do the MT soundings. They got the impedances from that, and then they move the whole array on. And their goal is to do the whole continent.
Do you know the spacing history between the receivers?
Pardon me?
The spacing history, those receivers.
Yeah, so if you know what that distance is, I don't know, was that 1,500 kilometers? Something, and then count dots, so maybe 100 kilometers between. They're trying to look deep. They're trying to get the large scale structure. So there's quite a few reasons for doing that. One is that on a continental scale, you just want to know how things are made up, right? The other is more of immediate practical consequences. I had told you before about this blackout in the eastern coast of the United States. Right? So you can imagine you got a power grid, okay? So maybe this is a couple hundred kilometers, around. So you got this, this power grid. Now you got this big solar storm that's coming in. So now I've got a vertical component of the magnetic field, right? So now you've got a huge magnetic flux that's coming in, time varying. And so that's going to induce voltages around here. So you're going to get currents that are going to flow through there. And that can be significant enough that it overrides whatever transformers protection you have. And that's actually what happened when in the late 1900s or 1990s, when we had that solar storm in the east, you got this surge, this voltage surge that went on this grid, and then just blew out these big transformers. And then they just pop like firecrackers going right, and they can't turn the currents off quickly enough to stop it, and it just basically took out the whole grid in New York and the eastern seaboard without power for 3 days. So they don't want to let that happen again. And in order to help mitigate these potential losses, they need to know what the electrical conductivity is of the upper 20 kilometers of the cross. And if they do that, then they can monitor they can decide what electric fields might happen if we had an auroral, some kind of auroral storm, and make sure that you're guarding against that. So that's another reason for trying to make sure you understand the electrical conductivity of the continent. And then water is a big problem everywhere. And I hadn't actually appreciated it before, but I guess the northern east part of Brazil, once you get inland from the coast, is a pretty dry area. Is that correct? I was talking to somebody last night. It just, I don't know, from my perspective, it always seems like Brazil is a tropical rainforest everywhere, but I don't know if that's not true. So there's areas that are dry. So we need to understand, where the water is and how it can be tapped. This is a section off of California. This is done, so it's a resistivity section, and it's that was used in a water project. We just came back from a conference in Denmark where they're looking at the potential for using electromagnetic airborne EM for all kinds of reasons. But a main one actually is water. And the state of California, Oregon, Wisconsin, they're kind of all realizing that they need to know what the subsurface structure is, at least in the top couple hundred meters, so that they can develop better hydrogeologic models of the Earth. In California, you always hear about these big storm floods that are coming through. So California is in a water shortage, it's a water drought. At the same time, there's times that there's just way too much water and everybody's getting flooded out, right? So it's like feast or famine. So perhaps where it's going to go, and this is what people are looking at, is that when you get these great big deluges of water, we're going to have to try to contain them somehow on the surface, and then contain them in areas where they could naturally drip through and permeate into the aquifer. That means you need to know what that upper region is and where should I build a dam? Should I build it over Roberto, or I should build it over at Lindsay? I get water that's coming in, dam it up, and have it in a place that it can percolate down. So that's kind of a long-term goal, but they're thinking of trying to fly airborne EM over much of the central part of California now to try to help characterize what's there. So there's lots of things with water. Saltwater intrusions are big things. We talked about pollutants. EM plays a big role there. And then physical properties, we talked about IP, the fact that electrical conductivity was dispersive. So that's got applications both in permafrost and sort of ice water problems. Looking at organic materials, there's some that definitely have a complex conductivity that's associated with them. So that means also there's bioremediation. So we can think about, certain kinds of bacteria or bugs kind of going into medium and changing the structure of that material so that the electrical conductivity is now frequency dependent, and that's an area of active research. There's a lot of work, especially in the European markets, looking at induced polarization as a direct indicator for hydraulic permeability. And again, we're going to see more. So this is conductivity being dispersive, but other probably like magnetic permeability can also be dispersive, depend on frequency. And certainly soils have that characteristic. We noticed that a lot. I've not talked about it here, but it's actually been associated with unexploded ordnance removal. Like there's lots of places around the world there's been military conflict and there's bombs and various things that are in the ground that are unexploded. And the question is, well, how do you find these? How do you find these things? Well, an unexploded ordnance is made of steel, so it's conductive and permeable. So some electromagnetic experiment can work. As a noise problem, some of the soils have a lot of magnetite of different grain size, and that actually causes magnetic susceptibility to be dispersive, and that can sometimes override the signal that you're looking for. So there's research to be done here, there's numerical modeling, and there's a lot of applications, which is a reason to be very optimistic about the need for looking at electromagnetics and seeing where it can go. And I talked about this. This was that kimberlite deposit, integrating multiple different kinds of data into a multi-physics property, and coming up with geologic models kind of directly from the geophysics. And the place that I think things will really take an important step forward is if we really make use of all of the web interactivity that is now becoming available. Geophysics is a small community, and if we continue to work kind of in our own silos and do things, we will make progress, but not nearly as much as if we all share and cooperate and work together. So open source and open source resources and collaborating, I think, is one of the most important things that that can come out of this, this next decade. And our efforts have really been in that regard. Everything that we've done, all of the apps, all of the resources, everything is open source. And that exists, and it can help people build on that material. Jaja is going to give a course. There's other people start to use that material. There's the development of both forward modeling and inversion codes that can be done through SIPE. The UBC group has done an awful lot of work on that, and there's other people that are contributing. But the more people who contribute, the more you gain personally, and the more that the group grows. So this was our efforts from UBC. There's also a group in Europe using Pi Gimli, and there's other places too. But just kind of changing your mode of operation to one where you think about yourself as being a member of a community working for the common good. It changes your perception and will make the field grow. And I think that's kind of where we are right now. And I'm looking very forward to the next 3 or 5 years to see how much further development that can be obtained. So developing code, putting it on GitHub, sharing it, working collectively, having the field grow, not rediscovering the wheels. I've been at the university long enough that I've seen many students come through, all of whom have been doing the same project, and then somebody comes through later and he needs to do this, and the existing code is spaghetti code, or he can't find it, so he ends up doing it himself. And then he finishes it up, manages to get a piece of code that can publish a paper, write pieces. Then that's gone. Then a few years later, somebody else comes on and he's repeating the wheel. We can't do that anymore. We need to move on beyond that, and that's where there's a large-scale future. And then we saw the other thing, and with the apps, we can look at Ward and Holman and these various textbooks, and we can see the equations. Sure, that's great, and you can manipulate the equations. You can maybe solve something, but you don't really learn from that. But if you have something like an app where you've got parameters that you can change, and you can visualize the fields and the fluxes, you can ask questions, that's when you really learn. And then once you understand, the fundamentals, or you can understand what kinds of signals make, then you can start to work really responsibly with that. And then you're not also in a position where you're overselling something, or you're not underestimating what the benefits would be. So the advances in computing power, and sharing, and developing visualization is huge. You just can learn so much, and you can advance so quickly by that. So as I say, our future collaboration, our efforts have been into developing EM GeoSci, this GPG for geophysics for the introducing, SimPeg, the simulation package. Those are our sort of contributions that we hope will promote further collaboration and contributions. So that was it. That was the goals of the course. We wanted to try to, inspire you, like just to see how EM could be used in potential applications, and importantly to kind of see the effectiveness through the case histories. And case histories are really important, because then you, like I said, it's a real problem, active situation, and you see what somebody was up against, what they did, how it worked, and if it works, it's great, you could use it. If it doesn't work, then you're like, oh, maybe I'll learn something. Maybe I won't want to repeat that same mistake. And just build on things. The other was to build a foundation. You need to understand the basics of EM. And we can explore those basics through our interactive apps and our resources. And I think the AdRock thing is a perfect example of that. Somebody comes along and they say, oh yeah, we can, but 10 centimeter accuracy at 1,000 feet depth, and we can use this EM wave and get the temperature. And like, what's the physics behind that, right? And what's going on? And if they tell you, well, sorry, this is all proprietary, it's top secret and stuff like that, I mean, we just don't advance that way. So we've got to understand the basics. We have to be able to know what physical equations are. We've got to know what the transmitter is, what the receiver is, what the process is, and then we make responsible decisions from that. And then once we know that, then that helps us set realistic expectations. Because we know we're not going to get 10 centimeter accuracy, right? It's just simply not going to happen. So those two things kind of go hand in hand. And then, the other goal is to try to, promote the development of the community, get people to contribute to open source software and capturing case histories. Jaja, we're expecting you to, contribute a lot now with your new course. And yeah, so our resources are the GeoSci website that looks like this. The web textbooks, our software, our apps, and we've got quite a few apps that you've already seen. More will be developed. The hard part in this is really like the development of that overall structure and trying to get that going. And this is where Lindsay and Saudi and Rowan and other people have been so important in actually getting that vision and really kind of making it. And once we got this sort of first pass through and have a place for everything, that's easier for everybody else to contribute. And I think that's kind of where we are at this point. And yeah, this has been a huge effort. I mean, if you actually really take a look at the total amount of material that we've presented over this week and all the material that's on the website, you'll see that that's an incredible amount of material that could not have been done with just a couple of people. There's a whole GeoSci team that is at UBC, and there's also been contributions through, from other people, especially Colorado School of Mines and University of Calgary. Anyway, everybody has contributed and has kind of got us to the point where we are right now. And so with that, I just want to thank you guys. I really appreciated the opportunity to be here. It's been a real pleasure. And, so I guess the only thing that we have left is we're trying to find a Korean-Mexican fusion food truck. Good luck. Okay, let's stick to margaritas.